Assalamualaikum warahmatullahi wabarakatuh. Today I'm going to present to you a hollow fiber carbon membrane which I synthesize using polyethylene oxide polymer for the use of oxygen and nitrogen suppression. In this study, I study for both single permeation and as well as mixture permeation. So the first slide, um, basically the oxygen nitrogen suppression is a very important component in process industries. Actually, we use nitrogen for food preservation and purify oxygen for boiler heating, to increase the efficiency of the heating. And we know that membrane separation is actually a state-of-the-art technology in gas separation of O2 and N2 because previously, we used conventional technologies such as cryogenic distillation and pressure swing adsorption. Yes, both processes can deliver main process objective, but it also consume large amount of energy. Besides, their very high complexity requires trained worker and rigid maintenance. But on the other hand, the membrane separation is capable of delivering of the same output with a minimum consumption of energy and also lower maintenance costs as well in the long run and also the short run. Well, the current problem, however, for the membrane separation is because of the polymeric materials which compromise too easy with extreme thermal and mechanical application. So if we want to install the membrane in our process, we requires to protect the membrane as well by having a pre-cooling and depressurization in order to prevent damage to the membrane. So that's why we are coming out with different materials made up of carbon membranes, made up of carbon. So we call it carbon membranes. Well, carbon membranes is not only sturdy but also capable of extending extreme condition up to more than 200 degrees Celsius. And besides that, it's also a very exceptional microstructures, enabling him to perform delicate discrimination between two gas molecules. And for example, oxygen and nitrogen. Both of these molecules have very small differences in terms of their kinetic diameters. And using a polymeric membrane is going to be very difficult, and the selectivity is very, very low. And currently, another important aspect is that so far the carbon membrane produced from the polymeric membrane has yet to establish any connection between the microstructure of the polymer and the microstructure of the carbon membrane as an end result. And so this caused an issue. What kind of polymer, what kind of structure polymer that can best produce carbon membrane. So there are many experiments, many modification on the carbon membrane by adding secondary materials and etc. So another issue is because most of the carbon membrane synthesized in the literature was not optimized. We do not know how far the performance can go. Sometimes it's just have a slight increase from the their pristine polymeric membrane. So that's why we need to find out how far the conversion from polymer to carbon membrane, which use very high process cost, requires high thermal treatment, really worth the process to obtain very high performance. So in this work, I try a new method that I try to use Robinson upper bound to establish an optimum point for the carbon membrane, because we know that one of the issues of the membrane is because of their tear-off behavior. It means that if we increase the permeability, the selectivity will decrease, and the other way around. So it's basically the theory says that improving both simultaneously is going very difficult. So in this work, I'm trying to improve both performance by using the Robinson upper bound mapping. Right, I will map all the performance on the Robinson upper bound, and from that I will select which one is the best, and I will go proceed for the next optimization. So this is the methodology. Firstly, we produce the polymeric membrane in the form of hollow fiber, and then we apply pyrolysis thermal treatment on the polymeric membrane in order to transform into a carbon membrane. And in the process, we varied pyrolysis temperature, heating rate, and as well as thermal soak time. And then we will perform tests and analysis based on their O2 and N2 permeability and as well as alloy selectivity. And we also run mixture process, mixture permeability, and we characterize some of them. And this is the important one, is mapping and selection of the best of the membrane, and we go for the next stage for optimization and so on. So this is how it looks. The polymeric membrane, we can see that the thickness is around 15.4 micrometers, and this is the morphology of the polymer membrane. So when we pyrolyze, the thickness decrease significantly, and the structure looks condensed and very dense due to the thermal treatment, and the approximated any diameter is decreased as well. This is the first test, which is we vary the pyrolysis temperatures, and as we can see that the red line is the oxygen permeability, the green line is the nitrogen permeability, and then the black line is the ideal selectivity between the oxygen and nitrogen. As we perform the pyrolysis temperature, as we can see that if we go for 500 degrees Celsius, the performance is actually lower than the polymeric membrane. This is what I said before. This is very important for us to investigate different types of parameters in the carbonization, because we may end up have a membrane poorer membrane in terms of performance. But when we increase to 600 degrees Celsius, there you go, we have an increase in performance, and in terms of permeability and as well as the selectivity. And then it decreases back when we further increase the temperature to 700 degrees Celsius. And when we map into the Robinson upper bound, we can see that clearly that the membrane with 700 degrees Celsius is the highest in terms amongst all. And the next one is the when we select the best and we go further for optimization in terms of the heating rate. As we can see, when we apply increasing heating rate, the permeability is increasing, and both for oxygen and nitrogen. But since the increasing rate is almost the same, we can see that the increment of the oxygen and nitrogen and the selectivity is quite stagnant. But we have a slight increase in here for the 4 degrees per minute, showing that this might be this show that there is increment in terms of oxygen permeability and as well as oxygen nitrogen permeability. So when we map this result in the mapping bond, we can see that the 4 degree per minute is the highest compared to the others. Even though the 4 degree per minute is in terms of permeability is lower than the 10 degree per minute. So we can see that this upper bound is very helpful in determining the best performance of the membrane we can have. So by selecting this 4 degree per minute as in our formulation, we go further into the optimization in terms of thermal soak time. You can see that from 0 hour until 2 hours. and we obviously see that there is a decreasing trend in terms of oxygen permeability as well as nitrogen permeability. This is as a result, the oxygen and nitrogen and their selectivity decrease very significantly. This is suggested by the previous work. This might be due to the thermal shrinkage that caused some pores to be closed. And so when we plot all this sample onto the horizontal bubble, you can see that the best performance is when we don't apply any thermal shock time on the carbon membrane. As you can see here, yes, without, if you don't apply the thermal shock time, is very superior in terms of the permeability and also the selectivity. So this is a comparison between before we enhance the carbon membrane and after we enhance the carbon membrane, and this is very there is a significant improvement using the classic optimization technique. And this is where we start as a carbon membrane when we gas the temperature 500 degrees Celsius and 15 minutes of thermal shock time. We also use 1 degree per minute. So when we optimize using the classic and also the mapping on the reverse upper bound, we can see that there's significant increase and we don't have to add any secondary materials onto the carbon membrane. If you compare from the previous works, there are a lot of carbon membrane that has been used from expensive polymers and some additional of secondary polymer, secondary material to the carbon membrane. And as we see that with simple classic automation technique, we can improve the productivity of the membrane we produce. And this is a very important findings in this study. And so as a conclusion, we can see that the carbon membrane performance can be enhanced significantly in terms of permeability and selectivity. And then the balance between those parameters we can amend to the best by using Robinson upper bound as the guideline, and as well as the commercial boundaries. And since I raised the issue about the threat behavior, and using this method we successfully improve the membrane performance without being affected by the trade-off behaviors. So thank you very much. You can contact me further using this email. Thank you.